direction. Okay, I think we're all good and we are recording. So, all right. So, welcome to the seminar. It's our first for the Middle and the speaker today's session is Ari here, and he's going to talk about fast detection of pollination events with these funny Tsetlin machines. Okay, it's all yours. Thank you.
Hi. Yes, I'd like to start off with showing y'all or asking y'all a little quick question. Please go to the next slide.
Oh, so it's not going to the next slide?
No.
Just go to the use the arrow key there. There. So yeah.
So we have a video for you. I'm just going to ask you the 10-second clip. How many pollination events do you think you can find in this clip? I'm just looking to see where a bee lands on a flower.
Okay, wait, I'm going to turn the lights down a little bit. Okay.
Oh, that was a spoiler. Okay.
They look for bees landing on flowers.
Yeah.
In real time. Yeah, it's real time.
We have any guesses? Any one from the audience? Okay. That's a good guess. Now back to where the spoiler.
These white dots are presumably bees.
It may be a bit easier to guess, like at that second pass, but it's closer to two. But I imagine that like only with a trained eye could you like sort of get that at first blush. And this is sort of like the core of our problem. We have a large amount of important entomological data that is difficult for humans to parse, and although with a bit of pre-processing, still difficult for computers to parse. Next slide. Mainly, entomologists are working on crucial conservation work. Specifically, they're working to look at how insects and pollinators interact with crop harvests and crop failures. They're looking at insect biodiversity in order to see using these insects as basal creatures for their environments, and also they're looking at food web studies where these insects provide are an important food source in their environments, and a lot of them rely on video data like the stuff that you've seen so far in order to actually do their work. Just to drive this point home, these videos, though difficult to parse, are fundamental to this important research. For a little bit of background on this data, most methods for studying insects, such as malaise traps or sticky traps, as sort of mentioned by Keisha before, involve a catch and kill method, where the insects that you are looking at must be captured in some way and then killed in order to actually study them. The alternative to this that is less disruptive to these environments is to use camera traps, where you sort of set a fixed camera in a position for a long time, like akin to a person in a ghillie suit with their camera, in order to collect long hours of data. And with larger animals, this data is easier to use, given that you can perhaps use a motion sensor in order to actually start and stop your capture. However, this is not the most accessible with insects, given how small they are and how imperceptible their motions are to a lot of sensors. So this leaves researchers with many hours, if not days, of field videos that they need to tag for events, interesting events, like let's say the pollination events that you saw in that first video of interest by hand. From experience, personally, it has taken me upwards of 12 hours to tag a video of interest that was simply an hour long. And I know that I'm no expert. I also know that I was not doing the best job, and 12 hours was probably underselling the amount of time that it may actually take people to work on this stuff. As this data is necessarily taken from the field, it is resultingly very, very noisy. We're looking at sort of how the wind rustles leaves in the background. We're looking at how changes in brightness affect how visible any of the actual insects of interest are able to be seen. And as a result, it just makes it hard for people to interact with this data, and sort of any tool that we could use to speed up this process would just be a lot of help for these researchers. Sort of here we can look at an example of just sort of like the type of noise that we're looking at. The brightness is fluctuating pretty intensely. There's like not the most stability in the frame for a lot of automation methods, and it also just makes it very hard to see the insects generally. If we can facilitate this research, we can save these researchers a great deal of time, and with the use of robust computer vision, we can potentially revolutionize this research. Time taken in order to do menial tagging will be slashed, and researchers who are dedicated solely to this task, mainly interns, can be reallocated towards more involved pursuits. Likewise, studies on insects, which, as we mentioned before, are important in a large variety of conservation tasks, can be scaled up in order to use this non-invasive method rather than the more accessible catch and kill methods at a larger scale. There are some tools that are already existing in order to aid in this camera tagging task, or this video tagging task. Most of them target very specific ways that the camera tagging or the video tagging task is quite difficult. Namely, there's Boris, which is a pipeline in order to physically make physically allow researchers to do manual tagging faster with hotkeys and a video playback function, but doesn't actually do anything to the videos themselves to make them easier to manage. Likewise, there's physical tagging methods where you, in exchange for the labor of tagging specific insects with, let's say, color or some sort of rectangular and easy to track tag, you can automate this process, such as anthrax or graphite. Likewise, there are some very simple background subtraction methods where you can remove the background of your image. But like we said before, we're dealing with noisy data, and typically this doesn't work the best unless you're working within very strict parameters for very laboratory conditions, or if you are working with larger animals who don't really have to deal with the effects of background noise. Finally, we look at the sort of most robust computer vision methods, such as deep meerkat, mega detector, HIDAT, which are able to perform this task quite well for this automation of tagging. However, they do so utilizing very large computer vision architectures, such as the inception networks or YOLO, essentially sacrificing time and speed of inference for this more robust capability. If we wanted, let's say, an ideal tool for tagging these insect and pollinator videos, we wanted to minimize the number of active hours that a researcher spends using it, automating as much of the process as possible. Likewise, such a tool should be very fast in and of itself in order to handle large volumes of videos, essentially working at the scale of large research projects. Tagging as a task in particular prioritizes as high a true positive detection rate as possible, essentially minimizing the number of missed missed events that are important to your research. And likewise, minimizing the false positive detection rate, essentially minimizing the number of fake events that you pick up, is less targeted, but still desirable to minimize the amount of time that a researcher may need to put in order to remove those from a final data set. Finally, if such a tool can be embedded directly onto a camera trap via a system on a chip, we can parallelize data collection and tagging. Likewise, this setup can reduce the power consumed during tagging, saving both time and power and leading to a better system overall. To meet these targets, I propose a pipeline consisting of a fast pre-processing step to minimize background noise and brightness variations, a background subtraction step on this normalized data in order to extract insects from a video, and a final detection step. One version of this moderated by a naive heuristic that's based on existing methods for detecting pollination events amongst entomologists, and one instead moderated by a Tsetlin machine trained to recognize pollination events. So looking at this first step, noise reduction, as mentioned before, because we're working at the scale of insects, this is a crucial step. Otherwise, all of your data is going to be quite garbled and unusable. Most of the noise that we're talking about due to wind can be removed with a simple final blur, simply just minimizing the amount that a green leaf moves over another green leaf, affecting the way that the final data is perceived. But noise stemming from changes in brightness is a bit more complicated. To do this quickly in the pipeline, I set the mean brightness of every frame to a fixed value to minimize large brightness differences across the whole video, and likewise subtract what I call a brightness model, similar to what is shown here, though not exactly the same. The brightness model being the sort of grayscale image to regularize differences in brightness across a frame and across little chunks of time. This highlights important edge information and likewise highlights smaller changes in brightness that may be caused by an insect flying rather than by the sun passing in between leaves. For the purpose of this task, with sort of the regularized video, we can use a couple of common background models. For the purpose of this project, I checked for common and fast ones held in the OpenCV library, namely the mixture of Gaussians, balloon variable kernel density estimation, a Bayesian-like model that's referred to primarily as a GMG, named after the people who published it, and pixel count thresholding model. I can go more into detail of this later if any of you have questions, but most of them work by using some method to create a background model and subtracting it from every frame. Next, we can talk about how we can actually take this sort of this extracted insect information or this extracted insect format and turn that into actual event tags. The first way, as mentioned before, is sort of a baseline that is based on existing methods for detecting pollination events by entomologists. A simple way to do this is, or the common way that entomologists do this is to simply look at when the head of the pollinator dips into the center of the flower. This can be quite simply replicated by instead looking at marking the center of a flower during an initial step in the video as our camera is static, and then when an insect blob or an extracted insect makes collision with that center, we can detect that as a pollination using some time thresholding as well in order to fine-tune that for actual insect behaviors.
What happens if the flower is waving in the breeze?
Oh, so when the flower is waving in the breeze, in order to do that, we simply just used a slightly larger radius around the center of the flower. The flowers themselves are that we were looking at are from the data that we're working with. The flowers were on a raspberry bush, and so the flowers were typically on like a more robust set of stems than the leaves were, and also given that they are typically a smaller size than the leaves, deal with movement due to wind a lot less. A more flexible model, more flexible method for detection than this is to use a Tsetlin machine or just machine learning in general. But here we talk about Tsetlin machines due to a number of characteristics that they have. Firstly, the Tsetlin machine is a machine learning model that's based entirely on classifying an input using only Boolean operations rather than more expensive floating point operations. Unlike a deep neural network, Tsetlin machine is very shallow and wide, consisting of a number of conjunctive clauses over the elements of the input, which are summed together and thresholded to determine whether an input is a member of a specific class. This combination of traits make the Tsetlin machine both very parallel and very easily implementable at the gate level for minimal power consumption. Essentially, you can put this on an FPGA and essentially put that FPGA on a camera so that if you have an input that you booleanized, let's say a frame of the video, pass it directly through with very little power consumption and at high speeds in order to classify that frame as including a pollination event or not including a pollination event. The convolutional Tsetlin machine is similar to convolutional neural networks. It's a version of the machine learning algorithm that's optimized specifically for matrices and for our purposes images. We can use by passing essentially a kernel input into or a moving kernel as input into our Tsetlin machine, we can perform several sub-inferences over the entirety of an image so that we do not necessarily need to care about the location of a specific insect in the frame in order to actually detect it. Given all this, we can discuss some of the evaluation, of this pipeline. So with the methodology just described, we can look at three important accuracy measurements for this pipeline. First, we can look at how each background subtractor performs using the naive pollination detection heuristic. For this, I will get the first metric on the top called percent events caught, which is the percentage of pollination events that are properly detected by the heuristic. Essentially, the percentage of events in your final spreadsheet that correlate directly to events in your true spreadsheet. The bottom left of the triangle, called the percent frames caught, this is the percentage of frames that are correctly categorized as either being a pollination frame or a non-pollination frame by your heuristic. Essentially, your most standard accuracy or your most standard frame accuracy. Finally, you have at the bottom right, your true positive accuracy. This is due to the task at hand being detecting pollination events. This is particularly important in order to prevent dropped events. This is the percentage of frames that are true pollination frames that are correctly categorized as so by your heuristic and by pipeline as a whole. In these two diagrams in particular, we're looking at the pipeline as it takes in a grayscale video. And for all the videos that we've discussed so far, they're the same set of two videos, either in color or grayscale, so far or going forward. As we can see here, you can see, all the models behave pretty consistently with regards to their total event accuracy, typically within the 80 to 100% range, or with the second video, typically in the slightly above 80%. Likewise, However, we can see that with regards to the percentage of, or the frame accuracy, that generally the CNT, the count-based background subtraction method, outperforms all the other background subtraction methods consistently. Likewise, we can see that in the sort of this red here, that the KNN style, or the balloon variable kernel density estimation background subtractor, typically performs better with regards to the true positive detection rate of the pollination frames. Moving forward to look at how this accuracy changes on color information, we can see that we can clearly see a substantial drop in the true positive pollination frame detection rate across all background subtractors. This seems to indicate specifically that a lot of noise that is stored within the color channels is affecting the rate at which our background subtractors are actually detecting true positive rates, and that would make a lot of sense given that a lot of the noise that we are able to target revolves around brightness specifically. And so the way that brightness can affect color in not the most regularizable ways is much harder to deal with in a fast manner. Next, we perform a runtime analysis again on those two videos in grayscale. Here we look at the number of iterations per second taken by 3 specific processes. The first is a normalization step, the normalization of the video as a whole, which is independent of what background subtractor used, and that is in gray. The remaining steps that we look at are the application of the heuristic in orange, and the foreground masking step, which is in blue for each respective background subtracting method. In actual terms of the pipeline, the foreground masking step occurs before the application of the heuristic. This is just sort of how the diagram showed up. We see that normalization is a consistent bottleneck, that it takes a bit more, or that only a bit more than 20 iterations per second can occur with the existing code. However, this is above the sampling rate, or above the frame rate of the videos that we're using, specifically 15 frames per second. So this could potentially work at slightly below real-time speeds, even with a bottleneck. Likewise, we can see that for all but the count-based heuristic, or all but the CNT-based heuristic application. I'm so sorry. Let me try again. All but for CNT, the application of the heuristic is really, really fast. We can see all these very, very fast orange bars that are doing upwards of 100 frames per second. However, with CNT, we can see that the application of the heuristic is much slower, a bit more than perhaps slightly below 30 frames per second. Despite this, CNT is specifically the fastest in the foreground masking step, doing about double the amount of frames of its competitors, and thus it's possible that the CNT-based background subtraction method would work particularly well with a much faster detection algorithm, specifically with the Tsetlin machine. Here again, we look at this same runtime analysis, but over color videos. Looking at the bottom axis and comparing it to the previous slide, we see that we're only capping out at 50 iterations per second here, while here we were going above 140. What you can quite clearly see here is that while normalization and while the background subtraction steps remain relatively consistent between both the gray videos and the color videos, the actual number of collisions or the actual application of the heuristic is much, much slower. This likewise could be, as said before, due to noise introduced with color information, specifically this noise creating a number of essentially false insect detections, which must be considered by the detection heuristic when looking for collisions with the flower centers. Finally is a comparison of the convolutional Tsetlin machine against the naive heuristic. This was done primarily in terms of the frame accuracy as using the library available for the convolutional Tsetlin machine. This was not the most, this was not immediately usable within the pipeline, as this library does not allow for the saving of models. So this essentially needed to be tested on its own using a data set. However, comparing both of these methods on the same data set, the convolutional Tsetlin machine was able to get a 92.6% frame accuracy rate. Essentially, 92.6% of frames were categorized accurately, while there was a 71.7% frame true positive rate. Essentially, 71.7% of pollination frames were correctly categorized. This indicates a slight underdetection of pollination frames, though likely with actual detection of pollination events, this will mean a typically high accuracy of events, given that most frames that are dropped are around the beginning or the end of a pollination event. Oh, yes?
Sorry, it's probably a very naive question, but how do you know about underdetection and overdetection? Because obviously, it's quite difficult to tell by eye.
Oh,
So how do you establish, what the machine learning should have done? Because sort of relative to what?
Oh, this is relative to a manually tagged set, actually. I worked with, the data set I was working with was tagged by Dr. Imogen Ryan, who was working on essentially a study of the effect of pollinator decline on crop yields, specifically of a type of English raspberry, and sort of using that as a ground truth, I was able to create this data set and do this comparison.
I see, right. So an expert human is the comparison.
Yeah.
Obviously, the expert human has had spent many hours doing all the, that makes sense.
Literally several issues of work.
Right.
And also working alongside an undergraduate named Sophie Penny, who also helped tag this data. Comparing this to the naive heuristic, we were only able to get a 75.6% frame accuracy and a slightly higher 76.6% frame true positive detection rate. However, given that the frame accuracy is substantially lower and the frame true positive is slightly higher, this seems to indicate that we have a very, very high over detection rate of pollination events. Essentially, a very high over detection of pollination events without actually getting a substantial increase in the number of true events that are actually found. So just given this, it seems like the convolutional Tsetlin machine, which was run in a pared down version in order to work sequentially, as it is a highly parallelized algorithm, and many complications arose with that I can discuss, that this would be able to behave much better at within an embedded system and in real time, given sort of a static, or a non-static, but like a useful fixed model. Likewise, in terms of runtime, the convolutional Tsetlin machine was able to run 21 inferences per second, while sort of like in this non-parallelized state and running sequentially on a CPU, with one inference per marked flower per frame. This gives to be about 2 frames per second on the data that we have. This is compared to the much faster naive heuristic, which was able to run at 26 frames per second. However, again, we're talking about running something that is meant to be run sort of deep and essentially entirely parallelly sequentially. And if embedded or at least sped up, I believe that this inference rate would increase drastically.
So since I'm trying to parse with understanding of frame accuracy versus frame true positive. So when you say 70% frame accuracy, it means of the set of frames which had events, you found 75% of them, and the remaining 25% you couldn't find them, right? Or what does it mean exactly, frame accuracy?
Oh, so the frame accuracy is essentially like the of the data set. It was able to categorize the pollination events or categorize, essentially classify into one of 2 classes.
Oh, okay.
With a 75% accuracy.
Okay.
Yeah, with a 75% accuracy, either to be a pollination event or to be not a pollination event.
Okay, and then the frame true positive was given that it said it's a frame, it's a pollination event, it tells you that you found actual pollination event.
Yes.
But it was just okay, so true positive is 26% of the frames you classified as pollination event were actually pollination events.
Yes.
So the product of the two is the number of sort of true positive. No, okay, I see that. Okay.
Or for the true positive rate, it's actually 76% of the actual true positive frames were detected by the either method.
Okay, so in the second number is the one that we care about, right?
The second number is the one that is.
So in that number, the Tsetlin machine underperformed. It doesn't do as well as the naive.
This is true. However, again, we're talking about frame accuracy specifically. When we're talking about tagging, it's most of the events that we care about. However, this isn't applicable with Tsetlin machines as they exist or coded in Python with existing libraries. However, given relatively or like slightly underperforming frame accuracy typically yields a much higher event detection accuracy because essentially near the ends of an event a frame might not be tagged that still will like give you the event as a whole essentially. Yeah. Now to discuss sort of extending this work beyond tagging. We're currently.
Sorry, I don't know if you can hear me. I had a question on the previous slide. What do you mean by a marked flower? I think I might have missed it, but when did you mark the flowers or track them? And is there any accuracy issue with finding flowers?
Oh, yeah. So we don't actually like physically mark the flowers. Essentially, just there's an initial step within this tool to essentially select regions of interest that you'd like to work with. So essentially, you just on a little image just pick out the centers of the flowers that you'd like to measure pollinations from. And essentially that gives you just a little location map of all the flowers and works with sort of our little collision detection for the naive heuristic.
Okay, thank you. Yep, thanks.
No problem. Yeah. So currently these methods are clearly we've talked a lot about the importance of this entomological data, and we've also talked about specifically how advancements in computer vision for this task are very important. And I think likewise it's important to talk about how these sort of methods are extensible beyond just the tagging task. For example, I, amongst others, I'm currently working on applying a similar pipeline to biomass estimation in order to replace more laborious and destructive catch and kill methods, such as shown with this image of sticky traps to the right, in order to give you more robust information about the biomass and biodiversity of a region without needing to substantially affect that population of insects. Likewise, adaptations can be made to measure things like insect flight patterns for more individualized studies, and also as shown with the HIDAT project mentioned before, as well as for non-invasive invertebrate classification for as a sort of as sort of like a secondary tool that's useful in a lot of different capacities. Finally, for summary and conclusions, I just like y'all to really, at the very least, like remember these three things. First and foremost is that entomology research is crucial for conservation. Insects have fundamental and diverse interactions within their ecosystems, and studying them during this period of environmental change with climate change is paramount. Second is that computer vision tools can help us conduct this entomology research at larger scales without disrupting important insect populations that we like to study, unlike with the most accessible current methods. Finally, that Tsetlin machines, though new, offer a promising path forward for creating these computer vision tools such that they can work faster, at lower energy, and directly in the field. Finally, just some acknowledgements. I'd like to thank my supervisor, Dr. Srinivas Keshav, as well as my co-supervisor in the zoology department, Dr. Lynn Dix. I'd like to also thank Dr. Imogen Ryan for all the aid that they were able to provide and all the tagging work that they did, as well as Darrell Denker, who I worked with to tag some of the, work with many hours with in order to tag some of the remaining data, as well as Dr. Ashok Thandarajan and Noki Bell at Cambridge for their support and funding. And finally, just some references for the stuff I've talked about, continued references and additional images that were not in those. Yeah, thank you. Questions? Even have a secret slide about how Tsetlin machines work.
Are you doing detection on individual frames or on video?
On video, but
You are doing, so the Tsetlin machine looks at many frames.
the Tsetlin machine currently only has the capacity or the Tsetlin machine just sort of like in its current format can really only do individual frame analysis. However, by essentially adapting the heuristic to include sort of like a Tsetlin machine alongside time thresholding, this would be applicable over essentially over larger time frames.
So what time frame did you consider, like adjacent frames or 10 frames or 100 frames? Or?
For the heuristic, I think the threshold that I ended up using was about 15 frames or about a second. But essentially, this was just to like prevent things like insect dropout in between frames, or like for like a split frame from affecting.
So it makes a prediction based on the last 15 frames. Is that the right way to interpret what you said?
For the 9 heuristic, yes.
What the Tsetlin machine does?
The Tsetlin machine can only do frame by frame analysis.
Oh, it's just doing frame by frame. Okay. And what's your frame rate?
Frame rate is 50 frames per second.
So for insects, so one thing that jumped to mind was there's these cameras that, have you seen these event cameras?
I don't believe that.
So instead of sending a normal camera would send you the whole frame, but you can get cameras that are designed at the kind of hardware level to only send you the differences.
Okay.
And then they can send data at hundreds and thousands of frames per second. So you'd get anything that was, and I don't know how much you can control the processing, but you might get an image out of the camera, which is very high frame rate of all the insects that are moving, right? You get the differences between frames sent to you, and that means a much higher frame rate. I just wonder whether that would help you in an application like this.
I believe that would, because also like you'd still like need to consider like the normalization step, because again, like with changes in brightness and with like the background leaves, like those are just a lot of.
Yeah, and I wonder whether you just get, it'd just be incredibly noisy. But there's a group at Toby Delbert in Zurich, he's done a lot of work on these event cameras and then putting neural networks after them. So did you compare it to, sorry, final question, did you compare it to a CNN?
I was planning on comparing it to a CNN, however, essentially like the time frame of the project not allowed.
What hardware are you running it on?
I was running it using so the most of it was run using essentially like Google Colab at the time. However, currently I'm running it on essentially like the desktop I have in my office. I'm not sure exactly the specs, but
the idea would be to deploy it in the field.
Yeah.
It's really interesting.
Other questions?
I'd be interested in seeing the extra slide.
Oh, okay.
666. So it just we need to commit a little crime and make it visible again. How do I unskip this?
I don't know, Google something.
I unskip this slide. Unskip it. Sick. Okay, cool. And slideshow. So Tsetlin machines, like at a fundamental level, just sort of consist of whether or not you want to include, or they can consist of conjunctive clauses that use sort of your input at sort of a binary level into sort of this machine, and in order to actively construct these conjunctive clauses for each clause you have specifically two of these little Tsetlin automatons or automata per each bit of input, and so this has sort of an even number of states. Essentially, if you're in the first half of states, that bit will be included within your clause, or if you're in the second half of states, the bit will not be included in the clause, and by essentially summing the final results of these clauses together, essentially just like a getting the number of yeses that you get, you can threshold that against some specific value to determine whether or not it is your input's a member of a single class. This is made a little bit more complicated by, like I said, there's two of these automata for each individual bit of input. Namely, the second automaton is supposed to include or exclude the inverse of that specific input bit. Likewise, half of the clauses themselves are not don't really say yes, this should be classified as, or this yes, this feature determines classification. They said no, this feature determines not classification, essentially. So you have a list of clauses that say yay, a list of clauses that say nay, and sort of a list of clauses that don't respond for any given input and say maybe, maybe not. And this is all thresholded together to give you your final output. As you can see, all these clauses are just side by side, and thus like no depth really happens. All of these can be run at the same time, more or less in a single operational step. Likewise, the actual training of these automata is a little bit involved, or just in a two-step process. The first more standard step is to use essentially like a randomized training set that's modulated by this value S, which is essentially your training rate, which will determine whether or not a specific automaton will be rewarded based on whether its output essentially is corroborated by the clause, or regardless of whether it's currently included or excluded. However, essentially once this is for essentially feedback system 1. Feedback system 2 is essentially if your model is already doing so well How are we sure, not necessarily sure that we're at some sort of like local maxima for accuracy? What if instead we try to essentially exclude as many, or like remove as many of our literals as possible from a clause in order to see how much we can pare down without sacrificing accuracy.
So this is a combination of backpropagation and aberration being done. So the upper one is backpropagation, lower is aberration.
Essentially, yeah. But sort of in this Boolean
Exactly, Boolean isolation rather than linear difference. You don't need to be differentiable, it's just purely logic.
It's true, precisely. Yeah.
It's a bit of black magic, I mean.
Yeah, I specifically run into issues where training can be extremely variable with Tsetlin machines, because it's specifically randomized.
Okay.
And it's not like randomized inputs every single sort of iteration is randomized, whether or not it will like actually include or exclude a literal, which means that like you could have like essentially like a single training step that gives you a very big jump into a much higher, essentially like into a much like higher realm of accuracy space, or you could have like a number of steps where pretty much nothing happens and you don't know why it's not getting better.
So the loss function is not monotone either. Right?
It's not.
Yeah. You get this upper oscillation.
Yeah, and this like adds complication with training, not necessarily with deployment specifically.
Yeah. Okay, any questions online? All right.
Hi. Yeah. Oh, sorry. I asked a question in the chat, but can the Tsetlin machine approach be extended to count multiple pollination events in a single frame? I might have missed this. Does it already do that?
So the way that this is done is by essentially like because with these pollination events, you know specifically where you want to detect them happening. We just send in a little snippet around sort of like that flower center in order to determine whether or not in order to sort of do that pollination detection on sort of like each sub image of interest.
Okay, got it.
Okay, great. Thank you very much, Sachin. Great, thank you. I will close the recording. You guys can speak. Now, this is how you stop the recording and then